Hi again. Today we're going to see about the thick cylinders and spheres. Yes, in that thing we're going to see thick cylinders. Okay, what is thin cylinders? Which is nothing but the thickness should be less than 1 by 20 than dia. So, அதோடைய thickness வந்து 1 by 20 விட கம்மியாக இருக்கணும் டயாவை கம்பேர் பண்ணும்போது. Like T by D which is less than 1 by 20 times. And we have seen that the stresses which is acting in the thin cylinder or hoop or circumferential stresses and longitudinal stresses are uniform and the radial stresses are neglected because of its small quantity. Okay, so நம்ம stresses பார்த்தோம் thin cylinders ல hoop or circumferential stress and longitudinal stress இது எல்லாமே யூனிஃபார்மாக இருந்தது. Radial stress நம்ம neglect பண்ணிட்டோம் because it is small. So coming back to the thick cylinders, T by D which is greater than 1 by 20 times. Here less than, here greater than. So stresses here are hoop stresses. Okay, the stresses which is produced in the thick cylinders are hoop stresses and it is not at all uniform across the thickness. So இங்கே வந்து uniform சொன்னோம், இங்கே வந்து hoop stresses will not be uniform. Maximum at inner circumferential, minimum at outer circumferential. Okay, like you can see here. So this is what the thick cylinder shell. So this is inner circumferential, this is outer circumferential. So inner means it will be maximum, outer means it will be minimum circumferential stress. Okay, okay, so this is what the diagram. This one inner circumferential radius is R1 and this is outer circumferential radius R2. You can see here, and this is the area, small area, so dx. So the inner length is, inner circumferential length is L, so outer will be L plus 2 dx, or we can easily say this dx as T. Okay. Next, longitudinal section. So I am just taking the longitudinal section, that is I am just dividing it like this, XX section. So it will be like this. Here you can see the pressure, bursting pressure will be acting like this. Okay, so opposite to this direction the hoop stress are acting, sigma x, and this is the distance 2x, it's a distance L, and this is the smallest area dx. Okay, so coming back to the bursting stress, so we are going to find the two things, hoop stress and the bursting force. Okay, so bursting force will be equal to Px into 2x into L, that is Px into this dimensions 2x into L. So this is what the area minus thickness part. Okay, so Px into 2x into L. So this is the pressure which is into this area, the whole area, minus, we need to minus this thickness part alone. So Px into this small thickness part. So Px into small dpx. Okay, into 2 times of x plus dx. This is the, here we have seen 2x, right? So instead of 2x, x plus dx, because it is for small distance for the thickness. So from the whole area I am just going to minus the thickness part, that's it, into length, this L, length. So here the pressure is Px, but here Px plus the small thickness part, dpx, and again into 2 times means 2x plus 2 dx, because this is small dx part, 2 dx into L. So இங்கே பார்த்தீங்கன்னா bursting forceங்கிறது வந்து total force எடுத்துக்கிறோம், total area P into the total area minus இது வந்து thickness partல இருக்கிறது, dx dpx இதெல்லாமே வந்து அதோட thickness partல இருக்கிறது. ஸோ px plus dpx thickness பார்ட்டை நம்ம ஆட் பண்ணிக்கிறோம். அதே மாதிரி இங்கே பார்த்தீங்கன்னா 2x plus 2dx 2 times of போட்டிருக்கேன். 2x plus 2dx 2dx means this thickness part into L. So by doing so you will get the answer. I'm just taking 2L as common and this is the thing. Next, so up to this it is equation number 1, okay, and this is the resisting force. Next, sigma which is equal to sigma into 2 times of dx into L. So this part dx into L, okay. So this is what second equation. Just equate these two equations, you will get the sigma x, okay, which is nothing but the stress, circumferential stress, okay. But here they are saying longitudinal stress is constant and independent of radius. So they are saying the sigma 2, I am just taking this longitudinal stress as sigma 2, this one is constant and it is independent of radius, okay, okay, and px will be radial compressive stress. Then sigma x we know that hoop or circumferential stress, and sigma 2 is nothing but the longitudinal stress. So longitudinal strain Ex will be equal to E2, we can write it as E2, okay, whatever may be the thing. E2 will be equal to sigma 2. இங்கே E2 வந்துச்சுன்னா sigma 2 மட்டும் பாசிட்டிவ்ல இருக்கும், மித்தது எல்லாமே நம்ம வந்து மியூவால் இன்ட்டு பண்ணுவோம் and mainly minus symbol போடுவோம், ஓகேங்களா. So E2 will be equal to sigma 2 will be positive by E minus of mu. We need to include this minus of mu in the other terms. So sigma x, this is for the circumferential and this is for the radial pressure. As you know, these two things are opposite to each other, acting opposite to each other, right? So I am just taking this as negative and this one as positive. So minus mu times of sigma x by E plus mu times of px by E. And in this thing we know that longitudinal strain, stress is constant, so strain is also constant. I am just equating this as here. These are all constant terms, right? E is constant, mu is constant and sigma 2 is also constant. So I am just taking these two things, px minus sigma x. So I am just reversing it. Sigma x minus px will be equal to constant, so I am just taking 2a, okay. Just substitute the values here, okay, and you will get it as x dp. So this is what the thing, and I am just taking it here. So 2a plus px which is equal to sigma x which is equal to the whole term, we have found it. And then just take the dp part here and dx part here. You can see here I am just taking this as aside and this x will come here, okay. So after that you can see here this part and this part is dp and this two parts are dx, right? So அதே மாதிரி just வந்து simplify பண்ணிட்டே வரணும். இங்கே dp part by dx அப்படியே வச்சிருக்கேன் நான். மித்ததெல்லாம் simplify பண்ணுறப்ப நீங்கள் பார்க்குறீங்க dp and இந்த பாட்டும் p ஓட part and this two parts are x ஓட parts, ஓகேங்களா. So just இதை இங்கே கொண்டு வரணும், இதை இங்கே கொண்டு வரணும், right? This dx will come here and this thing will come here. Just இது ரெண்டை மட்டும் interchange பண்ணிங்கன்னா you will get like this and just integrate it. So log of this one, because இதை வந்து நம்ம differentiate பண்ணால் இது கிடைக்கணும். So we can write it as log of denominator and this is integration. So I am just including log of b as a constant, okay, okay. Next thing, just two logs will get cancelled and this is the last thing, and after you reduce it you will get sigma x. This is nothing but the Lenz's equation. So this is what the important equations, do remember that. And in this equation a, b are calculated by boundary conditions, like at x is 0, at x is L. So by using those boundary condition you will easily find a, b, Okay, and the next topic is torsion. This is also an important topic. This topic, like, we are going to see about the shafts and springs. Shafts is for TNEB. The spring is for TRB. Okay, so we're going to see that. So first one, torsion on shaft. If shaft has torsion, means the two equal and opposite torques. So twisting forces are acting at the ends of the shaft to rotate it, right? At the ends or sides. So torque means what? Torque means force applied into the radius of shaft. And the main thing is the force should be tangential to the sides. Like this is as shaft means the twisting movements are acting. This torque is nothing but the force applied tangential to the ends into radius of shaft. So this is what the torque. Due to this torque, the shaft will produce a twisting movement. Like due to this torque, the shaft will produce a twisting movement. Shaft will produce a twisting moment, and this thing will cause shear stress and shear strain. So we are going to derive it, what is shear stress and how it is produced in the shaft. So the derivation of shear stress in the circular shaft subjected to the torsion. Okay, so you can see here, this is a shaft. This is the original one, like without applying the twisting moment. Okay, so this is a shaft, and one end is fixed and another end is free here, like it is a cantilever beam, and this is the length, and this part CD, which is nothing but the surface, the line on the surface. Okay, the line on the outer surface is CD. So this is circular shaft. Okay, this is the center point O, and this D is, I have mentioned it here. Okay, so as a result of torque, the CD will convert to CD dash. Like if you twist this D will come here, D dash. D will come to this position, D dash, right? So at an angle pi. Okay, so likewise I will mention it here as D to D dash. That is, the angle is theta. So we have two angles. Okay, this is for the center point O, D to O, D dash, and here it is for CD to CD dash. So two angles are produced. Okay, torsion due to T will be equal to D, D dash. So torsion will be equal to D, D dash, right? Because this is the displacement. Shear strain will be equal to distortion per unit length, like distortion by length. Distortion is nothing but dd dash by length. Okay, and here this length will be equal to CD, right? So I am just writing it as CD, which is nothing but the pi which is equal to dd dash by CD, opposite by hypotenuse, right? Sorry, this is tan pi. So tan pi means opposite by adjacent. Okay, so tan pi means opposite by adjacent. So we have got this tan pi which is nothing but the pi. Okay, so after that dd dash will be equal to so this is for the circular part. Okay, this is for circular, and this thing is for the whole shaft. Considering the whole shaft, C, D, D dash means this is the thing, and here this is a circular part, so D, D dash, O, right? So according to this, D, D dash will be equal to R into theta, like OD into theta, right? OD into theta. OD is nothing but R. So from this thing, we can easily equate this dd dash. So by equating, so you will get pi will be equal to r theta by L. Yes. So here we are including this modulus of rigidity, which is nothing but the stress by strain, shear stress by shear strain. Okay, so modulus of rigidity will be equal to shear stress by shear strain. We know the shear strain and stress is nothing but the tau. So we can easily found the tau will be equal to CR theta by L, and here the C theta L are constant. So tau is directly proportional to R. Yes, so we can easily say when the radius is 0, the tau is also 0, right, at the center point, shear stress. And as the radius is started to increasing, the tau is also increasing. So the shear stress at the inner surface will be minimum and the outer surface will be maximum. Okay, so they have made some assumptions here, that is the material should be uniform and the twist should be uniform and the circular section should be uniform, and then the cross section should be plain, remain plain before and after twist. As the same, the radii should be plain before and after twist. Okay, these are some assumptions. Okay, and the next thing is maximum torque transmitted by circular solid shaft, which is equal to pi by 16 tau d cube. Yes, this is the formula. So I am just writing those formulas here. So circular solid is this one, and hollow solid means you need to include two dia because outer dia and inner dia, right? Shallow means it will be like this. So you need to include two dias here. So this is the formula, pi by 16 tau into d cube. Here d naught power 4 by di power 4 by d naught means outer minus initial by outer. Okay, so this is the formula. And next comes the power transmitted by shafts. So I am just writing the formulas here. So power transmitted by shafts, which will be equal to 2 pi n by 60. So this is what the revolution per minute. Okay, so RPM of the shaft. Okay, revolutions per minute. So 2 pi n by 60 into T which is the torque cube. Okay, so here P will be equal to angular speed into torque. Okay, this is angular speed, which is nothing but the 2 pi n by 60. Okay, and the next thing is expression of torque in terms of polar moment. So we gonna see about the polar moment. Okay, so as you know, like the bending equation, there is a equation which is the same like T by J, which is equal to tau by R, which is equal to C theta by L. So here C is the modulus of rigidity and theta is the angle of twist and L is the length, and then tau, you know the tau, shear stress, and T is torque, and R is the radius, and J will be equal to the polar moment of inertia. Yes, this is polar moment of inertia. What is the polar moment of inertia? The moment of inertia of the area about an axis. So moment of inertia of an area which is about an axis, which is perpendicular to the plane of the figure, and it should pass through center of gravity. So for solid shaft, J is pi by 32 d power 4. Okay, so solid means only one d is included. So pi by 32 d power 4. For hollow shaft, J will be pi by 32 into d naught power 4 minus di power 4, that is dia outer and dia inner. Okay, so this is the formula for solid shaft and hollow shaft. Next we are going to see about the springs. Okay, so generally spring is a elastic body and which absorbs energy due to the resilience, that is it will come back to its original position. Okay, so that is what resilience. And third one is absorbed energy may be released when required. So it can release the energies which is absorbed whatever may be the time. So first வந்து spring அப்படினாவே elastic body. நம்மளுக்கு தெரியும் spring நாவே elastic body தான் இருக்கும். which absorbs energy due to the resilience. So அது come back, அது இப்படி விரியறது வந்து அதோட பொசிஷனுக்கு மறுபடியும் திரும்ப வந்துடும். ஸோ அதனால் வந்து இதை வந்து நம்ம ரிசைலன்ஸ்னு சொல்கிறோம். ரிசைலன்ஸ்னால் அது கம் பேக் டு இட்ஸ் பொசிஷன், அது திரும்ப அதோடைய ஒரிஜினல் பொசிஷனுக்கு வந்துடும். ஸோ அந்த மாதிரி தன்மை இருக்கிறதுனால இது வந்து எனர்ஜியை அப்சர்வ் பண்ணுது. அண்ட் அப்சர்வ்டு எனர்ஜி மே பி ரிலீஸ்ட் வென் ரெக்வயர்ட், அதுக்கு எப்போ தேவைப்படுதோ அப்போது இந்த எனர்ஜிஸ்லாம் ரிலீஸ் ஆகிடும். ஓகேங்களா? ஸோ திஸ் இஸ் வாட் ஸ்ப்ரிங். And what can we identify the best spring means capable of absorbing greater amount of energy for the given stress. Okay, it will absorb the greater amount of energy for the given stress without getting permanently distorted. That means it cannot be defeated, அதாவது அது வந்து கொலாப்ஸ் ஆகாது. ஸோ கொலாப்ஸ் ஆகாமல் greater amount of energy வந்து அப்சர்வ் பண்ணிக்கணும் நம்ம ஸ்ட்ரெஸ் கொடுக்குறப்ப. ஓகே, ஸோ திஸ் இஸ் வாட் த பெஸ்ட் ஸ்ப்ரிங். Spring are of two types, laminated leaf spring and then helical spring. Yes, two types. Okay, what is laminated leaf spring? Which nothing but it absorbs shocks in railways and road vehicles like that. So it is mainly provided in the places in railways or in the road vehicles, railway wagons and road vehicles, mainly in the materials vehicles. So to observe the shocks which is produced in the vehicles. Okay, so this is what the leaf spring, we will see that in detail. And helical spring means it is of closed and it is of open. So there are two types. Okay, closed coil helical spring, open coil helical spring. Okay, so laminated leaf means அது வந்து ஷாக்ஸ் ஒரு வண்டியில், எந்த வண்டியாக இருக்கட்டும், ரயில்வேவாக இருக்கட்டும் இல்லை ரயில்வேயில் போகிற வேகன்ஸாக இருக்கட்டும், வேகன்ஸ் மீன்ஸ் பெட்டிகள், ரயில்வே பெட்டியாக இருக்கட்டும் அல்லது ரோட் வெஹிக்கல்ஸ், அது கார், பஸ், ஸ்கூட்டர்ஸ் எதுவாக இருந்தாலுமே அதில் வந்து இந்த லீஃப் ஸ்ப்ரிங் வந்து நம்ம அட்டாச் பண்ணுறோம். எதுக்காகனா அந்த வெஹிக்கல்ஸில் வர ஷாக்ஸை வந்து கண்ட்ரோல் பண்ண, அதை அப்சர்வ் பண்ணிக்கும். ஸோ அதுக்காக. அதே மாதிரி ஹெலிக்கல் ஸ்ப்ரிங்கில் டூ டைப்ஸ் இருக்குது, ஓப்பன் coiled helical spring and closed coil helical spring. Okay, and so first we're going to see about the laminated or leaf spring. Okay, so this is what it looks. நிறைய பிளேட்ஸ் இருக்கும். ஓகேங்களா? ஸோ இந்த பிளேட்ஸ் எல்லாமே சேம் ரேடியஸில் இருக்குது. ஸோ இதோட பெண்டிங் பார்த்திங்கன்னா it will be same radius. Yes, and it has the same width also, but the length is different. The only difference is it has different length. ஓகேங்களா? ஸோ அதோட லென்த் மட்டும் டிஃப்ரெண்ட்டாக இருக்குது. And then this is the spring deflection. Yes, so here is the spring and it is also the axis of vehicle. Okay, so if this spring will have the deflections like this, so the spring will have the deflection like this. Yes, and another thing is we are applying W, a designed load at the bottom, like at the last plate, center of the last plate we are going to apply W here. Okay, if you apply W here means it will push the plates to be flat, right? If you apply the load here means it will push the plates to the flat. And then the only thing you want to know is the deflection will not be there, right? If these plates are moving forward means the deflection will not be there. Yes, so that's the thing I have said here. The spring is loaded with W. The plates will get straight and flat and the central deflection will disappear. Yes, the spring is like this. So if you apply the load, the spring also will get no deflections. It will come back to its normal position. Okay, and you can easily say this is the load means there will be two reactions here. So the two reaction will be opposite to this, and this load should be splitted to 2, right? Because it is acting at the center. So it will be splitted to 2 by 2, W by 2, W. And this is a length, L. That is spring span length. Yes, okay. So I'm just giving the notes here. B, which is width of plate. Yes, B is the width of plate and N is number of plates, and then L, as I said, the spring of span spring, and sigma is maximum bending stress, and then T is the thickness of each plate, and W is the point load, that is designed load. Yes, and del, which is nothing but the original deflection of the top spring. Okay, so the original deflection of spring. Okay, so up to this is clear, and we're going to see about the expressions. So expression for maximum bending stress. So first we're going to find this sigma, maximum bending stress derivation in the plate. Okay, so W is acting at the center of the last plate. Yes, the last plate is this, and the W is acting at the center. Bending moment will be equal to load into distance. We know load into distance is bending moment, right? So what is the load here? Just think this point. So they are just taking this point as a, they are just taking the bending moment at this point. So we can easily say W by 2 into L by 2, right? So W by 2 into half of the length, L by 2, will give you some answers, WL by 4. So just take this as 1. And then moment of inertia, that is I, will be equal to, normally the moment of inertia is BD cube by 12. This is what the rectangle. So you have to just change it as BT cube by 12. Okay. So what is the bending equation here? M by I will be equal to sigma by Y. Y is nothing but T by 2 or else D by 2. Okay. So Y is this. So M by I, which is equal to sigma by Y. So we know M, Y, I. Yes. So just substitute all the values here and you will get the sigma value as, so you will get the M as sigma BT square by 6. You can see here sigma BT square by 6. But the resisting moment by N times. So there will be N times because number of plates, right? So you need to multiply this N here. Okay, so this is what the second equation. So just equate these two equations. This is also a bending, this is also a bending moment. So just equate these two equations and you can see here you will get the sigma as 3WL by 2BT square N. This is the maximum stress developed in the spring. So this is the formula. Okay, and the next one is expression for central deflection of leaf spring. So you can see here, this is the thing, and we need to find the central deflection, that is this one. Okay, so we need to find this. So for the thing, this is all common. So A, B, half of the length, and this is C point, and it is the deflection. So up to this is common. Only thing we are adding is the origin O. So from O to A and O to D is R. R, which is nothing but the mean radius. Okay, so R is mean radius. So how about this thing? The full term, like O to this point is R. So this is deflection, right? So O to C is R minus del. So you can see here R is the plate to which it bends. So R is the plane to which is started to bend, right? So I'm just considering the triangle ACO. ACO. So like this. I'm just considering this triangle OAC, right? So what is this? R minus del, this is R and this one is L by 2. So as you can see, hypotenuse theorem, AO square will be equal to AC square plus CO square, right? So just substitute all the values here and then you will get the value del as L square by 8R. Okay, from this thing you will get the del value as L square by 8R. Okay, so again bending equation, sigma by Y, which is equal to E by R. So what is R? R, which is equal to EY by sigma. So here R is R, which is equal to EY by sigma, right? So what is Y here? Y is nothing but T by 2, right? So I'm just substituting this here. So R, which is equal to ET by 2 sigma. Just substitute this R in the deflection and you will get the answer. Sigma L square by 4 ET is the answer for the deflection. This is the central deflection of spring. Yes, so we have found the two things, deflections and then maximum stress. Okay, so next one is helical spring. So as we know, I just said two types are there, closed coiled helical spring, open coiled helical spring, right? And the next one, what is helical spring? Thick spring wires, so you know, thick spring wires which is coiled into the helical. The helical மேல thick spring wires நம்ம சுத்தி இருக்கோம். So that is what the helical spring. Yes? Okay. So we're going to see about the closed coil helical spring. Okay. So what is closed coil helical spring? So it will be like this. The closed coil helical spring. Yes. And this is the smallest dia. So it is very small actually. So D is the smallest D and P is also smallest one. P is nothing but the pitch distance between these two spring wires. Okay. So P is the pitch between the two adjacent sides. Yes. Okay. Helical angle. So if you note down some angles means it will be small. Okay. And W is the axial load. You can see here this is W, this is the axial load. And R is the mean radius. Okay. So due to this helical angle, the bending effect is reflected because it is very small and there is no bending effect. So bending effect is neglected and so it has only torsional stresses. So no bending stress but it has torsional stresses. Okay. So expression for maximum stress, shear stress induced in wire. So due to this torsional there will be shear stress, right? So what is that? We are going to see that. So D is what? Dia of spring. So this is the dia of spring. Okay. N is number of coils, R is mean radius and C is the modulus of rigidity. Tau is the maximum shear stress. Yes, tau is maximum shear stress and theta is the angle of twist and del is the deflect of spring. Okay, so theta is the angle and del is the deflections and L is the length of wire. So first one, twisting moment on wire will be W into R, like W into R. This is the bending moment. So load into distance. So twisting moment is over. And next, again we know that twisting moment will be equal to, there will be a formula, pi by 16 tau d cube. So this is the formula. So we know two twisting moments. So just equate it and you will get tau as 16W into R by pi d cube. So this is what the answer for the maximum shear stress. Okay. Okay. Next one, expression for deflection of spring. So we need to find the deflection. Yes. Length of one coil is pi d. Okay. So length of one coil is pi d or 2 pi r. So it's like a circle formula. Then total length of coil is, total length means number of coils are there. So what is it? Length into number of coils. So you will get 2 pi r into n. Right? So this is total length. Okay. Strain energy stored by torsion. Okay, so strain energy stored by torsion will be equal to U, which is equal to tau square by 4C into volume. So this is the formula. Tau square by 4C into volume. Okay. What is torsion? Torsion is produced in each wires. Yes. So torsion is produced in each wire. So you can easily say this torsion, we can easily write it as shear stress. Yes. So shear stress will be equal to, as we know, 16W into R by pi d cube. So this is what the thing, 16W into R square by pi d cube, the whole square. Why we have put whole square means here tau square, right? So the answer is 16W R, no square. So the 16W R by pi d cube. the whole square into volume is what? Area into length or height. Okay, so what is the area? Pi d square by 4, and we have found the length 2 pi r into n. Okay, so this is what the thing. So we can easily found by reducing it. So u will be equal to 32 w square r cube into n by c d power 4. Okay, so this is what the energy stored. Okay, so this is what the energy. Next one is work done on spring, which is equal to average load into deflection. Okay, so what is the average load? We know that W by 2 is the average load. Yes, because there will be two reactions. So W by 2, W by 2. So this is what the average load. Into deflection is del. Okay, so we know that we can easily found by equating these two things. So this is work done W. So W into U. So just equate half W del, which is equal to 32 W square R cube N by C D power 4. So by equating these two things, you will get the del as this one, 64 W R cube N by C D power 4. So this is what the del here. Okay, so we have found the maximum deflection. Next one, expression for stiffness. So here the only thing included is stiffness here. So stiffness, which is nothing but load by unit deflections. So we know the deflections, right? So just divide this deflection by the load. So W by deflection will be equal to CD power 4 by 64 R cube N. Just reverse it and remove this W. So you will get the S here, stiffness of spring. So up to this, spring is covered. Okay, so do watch all the videos, and next in the upcoming videos there will be more important topics will be coming. I think within 2 videos or 3 videos, I don't know, 2 I think. So in these 2 videos I am going to complete the strength of material. So do watch all the videos. Thank you.